Okay, now this part here we will be looking at superheat, or we are looking at simple Rankine cycle or superheat Rankine cycle. So this superheat and Rankine cycle and superheat Rankine cycle actually is the modification of what we have done earlier of your vapor Carnot cycle. So due to the impracticalities of Carnot cycle, that is why we have our Rankine and our superheat Rankine cycle. So in your Rankine cycle, it actually consists of a boiler. So this is your boiler. Okay, a boiler, a steam turbine. Okay, this is a generator. Then you have your condenser. I hope you can see the laser pointer. Okay, and then you have the pump, and then the supply of fuel. So first thing is your boiler. So for boiler, okay, the process that incorporated with the boiler is usually the isothermal or the constant pressure, isothermal and constant pressure heat addition. For boiler, you have constant pressure and isothermal heat addition. For turbine, for the steam turbine, you have isentropic expansion. The isentropic expansion for the steam turbine. And then for the condenser, you have isothermal and constant pressure heat rejection or cooling. Then for the pump, you have isentropic compression. So you have isentropic compression that builds up the pressure of the liquid, okay, up to the boiler pressure, So means heat supply, boiler, work output, steam turbine, cooling or heat rejection, condenser, work input, the pump. So on your TS diagram, this is your TS diagram, you can see that now your point 4 no longer sitting at this point. So before that, your Carnot cycle, you have your point 1 and this as your point 4. Now we have shifted the point 4 over to the saturated liquid line so that the pump can deal with only liquid, not mixture of vapor and liquid. So that means point 4 you have liquid, and then it undergoes isentropic compression to state point 5, where it enters the boiler at point 5, leaving the boiler at point 2. So from point 5 to point 1, you can see that it undergoes an isothermal process, constant pressure process. 5 to 1 is a constant pressure process, 1 to 2, and then to this line here. So this is your boiler pressure, and it is at constant pressure. And at the same time, point 1 to 2 here is isothermal. Okay, so then 2 to 3, you can see this line here from point 2 to point 3 is an isentropic expansion process that usually refers to the turbine. Then from point 3 to point 4, you have isothermal and constant pressure heat rejection that is based on the condenser. Then from point 4 to 5, it repeats the cycle all over again. Okay, so this higher pressure we call the boiler pressure, the lower pressure line we call the condenser pressure, and then we have the saturation temperature TH and the saturation temperature of TL. TH saturation temperature is based on the boiler pressure. TL saturation temperature is based on the condenser pressure. So from the properties table, okay, if you were to find TH, then you have to look at the boiler pressure and search for the saturation temperature at point 1. Okay, so it is at saturation temperature, and this one for TL you have to look at the condenser pressure, the TS, that means the temperature with the subscript S with the condenser pressure. So now to define each of these components, to look into each of these components, we call all these 4 components or 4 devices here, the boiler, the steam turbine, the condenser and the pump, they are all steady flow devices. Boiler, steam turbine, condenser, pump, they are all steady flow components. All steady flow components. So therefore, we have to refer to the steady flow energy equation. So first thing is we can look into 1, 2 or 5, 2, 2, 3 or 3, 4 or 4, 5. Any of these you can pick it up and then you can look at it first. So the first one I have picked up 2 to 3, that is the isentropic expansion process. Isentropic expansion process is actually based on the steam turbine. So when you refer to steady flow energy equation, you can see heat minus work is equals to the changes in potential energy plus the changes in kinetic energy, specific kinetic energy, and plus with the specific enthalpy. So since it's isentropic expansion process, so we say Q2 to 3 is neglected or negligible. So we can equate it to 0 or we can take it as 0. And then for the potential energy changes here, the specific potential energy changes, it is also neglected, okay, because usually we consider it as negligible. So it is also considered as 0. And then for kinetic energy, for steam turbine, okay, sometimes you have to include, but most of the time when we are solving questions on power plants, we neglect the kinetic energy as well for the steam turbine, okay, most of the time. But then you have your work done, that is your work output. So this is actually your work output is equals to the change of enthalpy alone. So your work 2 to 3, you can just take the changes in enthalpy from point 2, that is dry saturated vapor at boiler pressure, until it reaches point 3, which is the wet vapor at the condenser pressure. So now, since point 3 is wet vapor, so how to find H3? So first thing is you have to take S2, that is Sg, at pressure, boiler pressure, then find out S2, which is equals to Sg, then equate to S3, and then use your formula of SF equals SF plus X SFG to find out the dryness fraction at point 3, and then substitute it back into the enthalpy of H3 equals to HF3 plus X HFG3 to find out the H3 at point 3. So point 2, H2 is equals to Hg at boiler pressure. So if you can't catch up with what I am saying here, please watch the video again. So now the next thing is the condenser. So I have the condenser here. Condenser, condensation. Okay, so you have to convert, okay, the vapor back into liquid form. That means must be 100% liquid, because when it undergoes condensation, it has to undergo full cooling process. That means full condensation process. You cannot have a mixture of vapor and liquid actually. So that is why we bring point 4 back to the saturated liquid line, and that is one of the other reasons why, okay, it is impractical for Carnot cycle to be considered as in the power plant. So you have cooling liquid going at one end and then leaving at warm liquid, okay, because going in at point 3 actually is saturated vapor, that is from the condenser inlet. Where is the condenser inlet? So point 3 here is actually your condenser inlet. So it can be wet vapor here, or it can be dry saturated vapor, or it can be superheated vapor. So it depends on cases. Okay, so you have to depend on the questions. So going in is actually vapor, in vapor form, and then coming out must be in a saturated liquid form. Okay, so that is why you need cooling liquid to cool it down and to allow the vapor to condense and become liquid again. Okay, so this is also a steady flow energy device. So that is why you have to refer to steady flow energy equation as well. So this is steady flow energy equation. The points here can be changed on depending on which is inlet and which is the outlet. Usually we take outlet minus inlet. So Q3 to 4, that is the heat rejected, minus the work 3 to 4, which will be neglected, and then equals to the changes in specific potential energy, exit minus inlet, and then the specific kinetic energy, exit minus inlet, and then the enthalpy change of exit minus inlet. So in this case, condenser doesn't employ any shaft for its cooling process. So that is why the work done from 3 to 4 is being neglected. It's 3 to 4, not 2 to 3, sorry. Okay, it's work 3 to 4 equals to 0. Here I must do some changes. Okay, work 3 to 4 is 0. And then the changes in potential energy 3 to 4 as well, okay, can also be neglected. And then the changes in kinetic energy 3 to 4 also can also be neglected. So therefore, when you neglect all these three terms here, so you have only heat 3 to 4 is equals to H4 minus H3. So I will teach you how to find H4, H3, H1 and H2 later. So the next component or the next device is your feed pump. So when you refer to feed pump, okay, so the purpose is to, okay, raise up the pressure of the saturated liquid until it reaches the boiler pressure. Okay, so it involves isentropic compression process. So you cannot neglect work done for this case because it's dealing with work. For condenser, you cannot neglect heat because it's dealing with heat energy. For turbine, you cannot neglect the work output or the work because it's dealing with power output or work output. So isentropic compression for the feed pump, okay, Q4 to 5, W4 to 5 equals to the changes in specific potential energy plus the specific changes in kinetic energy plus the specific changes in enthalpy from 4 to 5. I've told you, okay, that the changes or the heat loss here can be considered negligible theoretically. Okay, so that is why, okay, and then it is considered as an isentropic compression. Isentropic means no heat flow. So therefore, you consider Q4 to 5 as equals to 0. Usually the turbine and compressor, we assume it as isentropic expansion or compression, but in real life, there is a certain amount of heat energy loss. There is a certain amount of energy loss due to heat transfer. So that is in real life, in actual case. But theoretically, we assume that it is perfect isentropic. Perfect isentropic, that means there is totally no heat flow or no heat transfer here. So negligible changes in potential, specific potential energy as well, and also neglect the changes in specific kinetic energy. So it arrives to work 4 to 5 is equals to H5 minus H4. Remember, it's always the final point minus the initial point. So from here, okay, most of the time you will get a negative sign. In order to prevent from getting a negative sign, you can always, instead of taking the exit minus the inlet, you can take the maximum minus the minimum. So you have always a positive magnitude. But then remember, for a pump where it undergoes a compression process is considered as a work input. Okay, work output is when the system undergoes expansion. Okay, so that is our sign convention that we consider work out positive, work in is negative. Actually, you can also consider work out to be negative and work out to be negative, work in to be positive. That is explained as because work out is energy out, so from the system. So that is why in certain cases it's actually depending on you. But then you don't confuse with your negative and positive sign, because it only shows you the input and the output only. Okay, now so you have that. So from here you get the next thing is the boiler. So this is a boiler. Now so point 5 is where your point, your inlet point, and point 2 is where your exit point is. So inlet, saturated liquid from the feed pump. Outlet is dry saturated vapor. We try to get the vapor or the steam until it get dry saturated. That is the best effect. Okay, so sometimes you will get, or most of the time you will get wet vapor as well. But okay, it is better for us to consider that it reaches the dry saturated vapor point. And sometimes it might be superheated, sometimes it might be reheated. Why it is superheated or reheated is because it tends to improve the quality of the steam at the turbine exit. Second thing is to improve the efficiency of the whole power plant. So again, from your steady flow energy equation, now this is considered as a constant pressure, or at certain portion is considered as isothermal heat addition, but most of the time is considered as constant pressure heat addition. And this is your steady flow energy equation. Remember, boiler heat energy is the most important thing, so don't neglect your heat, but you can neglect your work if you were to consider that there is no work because due to no shaft. Then you can neglect the specific changes in potential energy and the specific changes in kinetic energy. So when you neglect these three forms of energy, then basically your steady flow energy equation will arrive at H2 minus H5. Enthalpy at 0.2 minus the enthalpy at 0.5. Okay? So you can always remember that maximum minus minimum, and then this is heat supply, heat energy input to the system. So that's why we should consider positive. Okay? Now, there are ways of increasing the thermal efficiency of a Rankine cycle. There are many ways. Okay, first of it is lowering the condenser pressure. Lowering the condenser pressure, okay, that is by lowering the average temperature, the saturation temperature. Okay, lowering the operating pressure of the condenser automatically will lower the temperature of the steam. Second point, superheating or reheating it to higher temperature. Superheating it to higher temperature to improve the thermal efficiency or the cycle efficiency, or also improve the quality of the steam at the turbine outlet or the turbine exit. Then increasing the boiler pressure. That is the next point. Increasing the boiler pressure also will help you to improve the thermal efficiency. Increasing the average temperature during the heat addition process is to increase the operating pressure of the boiler. Okay, so that it is for Rankine cycle. So here we have a few quizzes. Okay, so let's do together. First, which of the following cycles has the maximum thermal efficiency for a given range of temperature? Never mind. Now only you come and tell me. Okay, now which of the following cycles has the maximum thermal efficiency for a given range of temperature? So Carnot cycle, that is the answer. Halimi, make me no mood. Now, during which one of the processes heat is added in the Rankine vapor power cycle? Is the reversible constant pressure process. Then due to which one of the following reasons Rankine vapor power cycle is considered as the most practical cycle? Heat addition at constant pressure process. 4. The ideal cycle on which a steam engine works, that is the Rankine cycle. Rankine cycle comprises of, that means includes 2 constant pressure process or isobaric and 2 isentropic or adiabatic. 6. The Rankine cycle as compared to Carnot cycle has high work ratio. Okay, that is your tutorial. That is for you to do it, okay, in the later. Okay, but then I will show you the working of this later on. Okay, so thank you very much. Thank you very much. Thank you.